Okay, so good morning, and I'm beginning what I think will be the start of the last couple of lectures, maybe one or two lectures, where we're going to study the magnetic properties of a Fermi gas, and so we will see things which go with names, but it may look fancy, but it's not that fancy. It's all within what we have done. So Landau diagmagnetism. So this is just the fact that a gas of electrons will have a diamagnetic, that means the magnetic susceptibility will be negative. Okay, there'll be one contribution from that. Of course, the spin will couple to external magnetic fields, and that's paramagnetism, but in this context, it's called Pauli paramagnetism. So we have done isolated spins, but here what we have is a gas of fermions, each of which is spin half particle, so that will also be there. And so this diamagnetism is a high temperature, but there's a very interesting effect which happens at zero temperature itself, and that's called the de Haas Van Halfen effect. Again, that's just how the susceptibility has discontinuous and the magnetization has discontinuous chunks. Okay, so these are the three different characteristics, and the cool part is that we know the technology to prove all these things. Nothing very, very deep. Okay. So let's get started. And so first we will just consider a single electron in a magnetic field. Okay, it's just some notation. M here is just mass of the electron. And E is the charge of the electron. Okay, so the Hamiltonian plus there is this spin coupling, which is G times the Bohr magneton, I guess, times S dot B, and I have to divide by an H bar because there's an H bar in this thing. Okay, so this is the, if you wish, the orbital coupling. And this is the spin coupling. Okay, and so this is this would be the full Hamiltonian. But for today's lecture, I will kind of ignore the spin part. We can do all of them together, but it just becomes a mess. So we will do only the first part. So one thing we saw was classically there can be no magnetic response. Okay, so basically what happens is that if you do the partition function, because it's just shift in the Gaussian, so shift in P, you will have an integral d cubed x d cubed P times e power minus beta h. So there's no spin at this point. And so then you can see that the partition function is independent of the magnetic field. So magnetization will be one derivative of some free energy, and susceptibility will be one derivative or two derivatives of B, but there's no dependence on B. So the answer is 0. Okay, and this has a name. This is a theorem due to Bohr and Van Leeuwen. When U and V look the same, but sorry. So this is what we have. So very clear that any magnetic effect, be it orbital or spin, of course is already a quantum mechanical object. It's not something is you cannot picture an electron spinning because it's spin half. You'll never get that. Okay, so today we study quantum aspects. Okay, and and further we will, we only focus on the first term for now. Okay, so H for us will be just 1 by 2m. Okay, so in principle, in your quantum mechanics course, you should have done the quantization of this okay, and you should, but you have not. I know that. Okay, you should or not. I don't know. Have seen the quantization or the spectrum, of a charged particle in a magnetic field. Okay, but since you have not seen it, it's okay. I'll give you the spectrum and describe it. And I think I put up something on Moodle where we can derive, you can get the exact wave functions, etc. But the spectrum, so the problem is that we'll take B vector to be some constant B aligned along the Z direction. Okay, and and our sample, we will just assume that the electron is in some kind of sample. I'm drawing it like a cylinder, but it could have any cross section. That's okay. Okay, so this area xy, so this is Z direction, and x and y are this way. Area, this is in the xy plane, is A, and this the length is L. Okay, so this is the Z direction. Of the cylinder which I have drawn. Okay. The sample need not be, exactly. It could be square. It could be anything. Okay. So this is a rough picture that we have, and okay. So the energy levels, okay, they depend on only two sets of things. One is kz, and there's a second quantum number n with subscript L, which I'll explain in a moment. L for Landau. Okay, and there are other parameters, alpha, okay, on which the energy doesn't depend. Okay, so okay, so and what is omega c? It is the cyclotron frequency. So what is cyclotron frequency? EB upon m, right? Cyclotron frequency. If you have any questions, you can ask anytime. Okay? And so we can now look at the two terms. So let's call them 1 and 2, and I'll explain them. Okay, so this term is 1, and this term I'll call it 2. Okay, so let's look at what 1 is. 1 is just like there is no magnetic force, nothing. It's like a free particle. Okay, so it's just, oh, it's h cross square, right? Not h cross. Okay, so free motion. Along the z-axis. And for obvious reasons, it doesn't depend on the magnetic field, nothing, right? So that would be, and that should not matter for our magnetic properties. Okay, but in principle, that is there. Okay, and second one, this one is the interesting one, and so it looks like some as if that's an effective harmonic oscillator kind of thing. Okay, so NL goes from 0, 1, 2, 3, so on and so forth. And here, of course, Kz belongs to R. Takes all real values, minus infinity to plus infinity. And later I'll work with Pz, which is just H bar K. Z. Okay, so NL is exactly like this. And L stands for Landau. Okay, L subscript is to remind you, it's called the NL is called the Landau level number. Okay, and yeah. Good question. So it depends on your units. So in SI units, I think there is no C, and in Gaussian units, there is a C. So here is the way to remember it. You take your SI formula, and wherever you see either A, the vector potential, or B, you replace it by C, divide by C. Okay. And the other change you have to do is 4 pi epsilon naught, you put it equal to 1. Or wherever you see epsilon naught, put 1 by 4 pi. Okay, so that's what works. Okay, only these two things will take you from SI to Gaussian units. Okay, so yeah, so don't get confused. So if there is a C here, for instance, the book I'm looking at, Person Wang, works in Gaussian units. Okay, so NL is called the Landau level. But the point here is that there is important thing here is that there's an enormous degeneracy. Okay, so fix. First thing is, let me just say that we will, okay. So for fixed Kz, okay, I should fix Kz because I can vary Kz is some continuous number. I can vary and get any this thing. And fixed NL. There is an enormous degeneracy. Okay, which is labeled by just a random number, actually, alpha, which runs from 1 to G, where G is the degeneracy. But I have to tell you what is the degeneracy. Okay, what is G? Okay, so I'll give you an answer which is different from what is there in the problem set that I have given. Okay, so you let phi, which is B times the area. What is this? B is the magnetic field and this is a cross-sectional area, so that's the flux. So this is equal to magnetic flux through the sample. Okay, total magnetic flux through the sample. That's what this is. But it turns out that there's another quantity, which I'll call phi naught, which turns out to be the basic, it's a quantum of magnetic flux. Okay, and it's given in terms of two fundamental constants, H and E. Okay, So what it says is that quantum mechanically flux is quantized. There are a lot of effects due to this. And so G tilde I'll define to be capital phi upon phi naught. So what is this? This is just the number of flux quanta. Okay, that's a nice geometric interpretation. Is that this degeneracy can be understood in classical terms in terms of the smallest orbit, how many you can fit. So a classical thing at with NL equal to 0, that means the energy is half h cross omega c. That will give you classically for that energy, you'll get a radius for the particle moving in the plane, xy plane. And if you work out that radius and take pi r square of that thing, then and divide by the area, you will get what you will get is you'll get whatever I'm writing. Okay, so this is the number of flux quanta, and G will be 2 times G tilde. Okay, so this is just a spin degeneracy. I'm not working without spin. I'm ignoring the spin part of it. I mean, don't lose sleep over whether we are using 2 or not. Okay, so I want to be. I mean, you cannot quite turn off the spin of the electron; it's still there. So because if you're using Pauli exclusion principle, which we will do, for instance, at t equal to 0, you have to fill things up. So you will keep going up in energy, but then if you just wanted to find out what the Fermi energy is, you would miss the fact that there is a spin degree of freedom. So we need to put that. Okay, so only for that sort of a thing. So this is what is going on, and I just want to make a remark: is that there are SI units is based on some standards. And over the years, so for instance, the original thing in my childhood was that a meter was defined to be, the length of a rod lying somewhere in some France. Okay, and people made copies of it, etc. But nowadays, we need much more accuracy than those kind of standards, because we can measure things so that if, whatever material you have, how much ever it's protected, it might lose a few atoms here and there. And we are reaching situations where we need accuracies which are much, much more than that. I mean, for instance, now we have reached a point where we are able to, even detect gravitational waves. So you can see that, things have progressed. So these kind of physical standards are useless. So they've been moving away. So for instance, what was done for, so length was traded for, length of a rod in Paris, I guess, was replaced by you fix the speed of light. To a particular value. Okay, and of course, if we are starting from a scratch or something, we could have just said it is, nice round 3 into 10 power 8 or something. You can't do that because previous experiments, etc. So you stop at some. So I think, I don't know how many, some 10 or 15 decimal places. You can check up the size thing. So C is defined to be that thing to that precision. Okay. Similarly, mass of a of a sphere in Paris or whatever, right? Yeah. Gone to sleep? This is okay. This is okay. How can it go to sleep? Just 1 second. It may get hot sometimes, I guess. What is it showing there? Now? Meanwhile, you can see both, right? Beautiful. On back to blue. I'm feeling it's gotten too hot. Here you come. Why do people come to that? Oh, this is bad. Okay, sorry. So now that the screen is back, I can resume the lecture. Okay, so the mass of a sphere in Paris is now replaced by setting Planck's constant h to a particular value. Okay, and this happened only in 2019. This happened earlier, but this is the change. So it's moving to where you fix various constants, h, c, etc. But now you said, how does c become a length? Then you need to have a time scale set, and time is 1 second is defined as some, I think, cesium frequency of some line. So many cycles of it will be in how many cycles, so that is defined. So everything is moving away from into something which is much, much more robust. Okay, so this is what has happened. And the thing is that similarly, charge of the electron, Boltzmann's constant. So please look up this. There's a lot of interesting things, a lot of discussion, which I think you people are now primed to understand why they are doing these things. Okay, so so the quanta of flux in some ways is h and e are fundamental constants. So this phi naught is something which you can measure in some ways. So this is the degeneracy. Okay, so this is what is going on, and now we can just go ahead and we can compute. So the grand partition function from which we can derive magnetization and chi. Okay, so let me just write some formulae. So the magnetization is kBt times d log of q by dB, I think. I'll check if there are some more things. Of course, this is done at constant, what are all the things? Temperature, volume, and Z or mu. Okay, this is dm by dB, and it's usually defined at b equal to 0. Okay, let me check if my formulae are correct. Somewhere I had written it. Good. Okay, so these are so if you compute q, we can take d log of it, and then we can just go ahead and look it up. Okay, so what is q? It's product over all states. Okay, and for each thing we think of it as a box and it's fermions, so that may only 1 and 0. These are the only, rather 0 occupancy, which will give a 1 plus single particle e power minus beta epsilon, and N, which is the energy of the state. Epsilon here is the energy of the state. For? No, everything is there. No, I'm not fixed kz or anything. It'll come as an integral. I just made it's like, in a movie theater, halfway they'll say coming attractions soon, the theater near you. That way it's like coming attractions. Eventually this will not contribute that way. Okay, so we need to do this. But what is this product over all states? Is product over all values of kz. Okay, then product over all values of NL. Okay, and product over all alpha, which is the degeneracy for fixed kz and fixed NL in this order. This is okay. So this just requires not many deep details beyond, what we wrote here. Okay. So now I can just go ahead. It is there. Alpha is that index. Alpha goes from 1 to G. Okay. So that's the thing. So now we can write. Now I can do better. So Q. And let me just do log Q itself. Okay. Because then product becomes summation. Okay. I'll write summation kz and pretty soon we'll convert it to integral over P. Okay. I'm just putting alpha is there, but even though energy doesn't depend on alpha. Okay. So we can do that. And now we can see certain. So first thing is, so let's simplify things a little bit more. So we can replace the summation over kz by the semi-classical thing, which would be integral dpz dz upon h. But dz integral, it goes from 0 to L. Okay, so we can replace this with L by h rather, integral minus infinity to plus infinity dpz. It's a semi-classical answer. Okay, and then this replace by a factor of G, since energy is independent of alpha. Yeah, but the semi-classical formula density, yeah, that's correct. So, but we have to integrate kz. So we have to sum over. So if it's, you have to put some boundary condition, kz will be discrete, right? So what we want to do is to replace that with something where we can do the semi-classical formula. Don't bother about the exact discrete. No, this is not exact because it will get messed up, at the low level values of k. We saw how the semi-classical agrees for large quantum numbers, but not for small. So this is an approximation, but it's a decent, good enough approximation for many things. Okay, but when we messed up, for instance, Bose-Einstein condensation was one example where we actually had to say, oh, we couldn't replace it. We needed to pull out what we are doing is replacing a summation by an integral. Okay. And so obviously they're not equal to each other. And so we put the zeroth guy by hand, a separate term. And then it didn't matter whether we, put zero, it was some integral from 0 to infinity, but it should have been, correctly speaking, epsilon, where epsilon is equal to the first excited state. But as in the thermodynamic limit, that goes to 0, so it doesn't matter. But that the fact that that term which is missing, so the correct answer is you have to do the summation, but then you can't really do all that. and you won't need something beyond that. Okay, so any other questions? Yeah, actually, this is a good question. Why are we doing it? Okay, so this is semi-classical. Okay, so now we are ready. Log Q equals to L by H. Okay, and then we can write a G. Okay, summation. Forgot the integration first. Okay, so we got log Q now. Okay, of course we still have. So now we have to look where are all the B occurring. Where is the terms involving B occurring? Okay, one is in omega C, right? But there's a second point, the second place where it is there. Where is that? In G. Okay, recall G was equal to 2 times B times A upon 5, which was H by 2E. Okay, so a nice thing happens. You see that A comes here. So if you plug in the value for G, A times L becomes the volume of the sample. It's kind of cool. So let's put all these things together. So it will become 1 by V. Let's take V to the other side. 1 by V log Q becomes applied 4 E B by H square. Okay, so this is what we have. So this is first formula. Okay, and the second formula we want is to relate the number n. Okay, in terms so this is so the n will be given in terms of it's similar to the same thing what we have here, but it will be just I think it's 4 E. Hopefully, I'll write out something and then. Okay, so this is just a Fermi distribution function, but we can go ahead and if you want take d log z log q by mu etc. You will get the same formula. Okay, I'm just jumping. These are the standard things that we did earlier. Okay, and epsilon of course contains. Okay, so these are the formulae that we have. Now we can go ahead and compute. But what I'm going to do is I want to compute things at high temperatures, so there'll be a simplification. Can't sit there and do this integration. I don't think we can do summation. It's a mess. Okay. So this is the high temperature limit. Okay, and what is it we know at high temperatures? So what we will see is that chi, okay, goes as 1 by the temperature, that's a constant, and crucial, that's a minus sign. Okay, so it's the Curie law. 1 by T at high temperatures, magnetic susceptibility. Okay. By the way, which Curie is referred to here? Pierre Curie. Okay. The less famous Curie. Okay. Okay. So we will see. This is what we'll prove. Okay. So at as t tends to 0, t tends to infinity, or large T. Okay. Z. So one more thing we know about the forming gas is that it becomes more and more negative. It becomes the same as we even have worked out what Z is in terms of it matches the ideal gas story. Okay, so we know that, and so if mu is large and negative and large, Z will become 0. Okay, so Z goes to small. Okay, so that is one thing. Of course, beta goes to 0 as well. Okay, so let's look here what happens. Okay, and so we have 1 plus Z times the energy, e power something, and beta is small. So really Z is the operating thing. So you can see that. Okay, so this implies that Z e power minus beta epsilon is small. Okay, so that means okay, so then what we have is log of 1 plus x is equal to x plus order x square. We're interested only in small things. Okay, so what does that mean? It just says that you replace this whole log by just this term. Okay, so this implies that log 1 by v log q equal to 4EB by h square integral dpz summation NL equal to 0 infinity times this quantity, which is Z that's what we get. Okay, higher order terms we throw away. Now we can do this integration. Okay. Further, let us look at n also. You can see that n becomes log q. Okay, how do we see that? You come here, and if Z is small, Z inverse is very large. Okay, so that means you can drop the 1 here, and you get 1 by Z inverse e power my beta. This thing, that's just exactly what we have here. Okay, so this is so I'll pause here. Are there any questions or comments? What? No. Log q goes as V, so this is 1 by V. Sorry. Yeah, you're right. Because I messed up here. Okay. So now we can see, right? So you can look here. So these are very simple sums to do. So integration over Pz. It's a Gaussian. integral and sum over NL. And if you remember, it's just NL, so it's just this thing, geometric series. Okay, so I'll just write the result. Okay, so it's is it okay if I don't go in the details? I'll just look up the answer and write it. Okay, because I'm sure I will not remember the root pi's and all those things. This is Gaussian integral, and this is just a geometric series. Okay, so what we get? Sorry, I just have to correct on what they have here. So this is a magnetic thing, mu b dot this thing divided by 1 by kb. Okay, so high temperatures, so X is much than 1. Okay, so this is what we get. So you can see this is a Gaussian integral and this is the geometric series. So we are almost done with this. And okay, but now what we want is we want to evaluate. So we want to take up to 2 derivatives of log q. And one derivative will give you n, this thing. So we should work to order b square. So we'll work for weak magnetic fields. And okay. Up to order. X square or b. And including, okay. So if we just do that, what we get again, okay, so you see here there's already a b in front, so we just need to work these things to linear order in X. Okay, so this will be e power minus X can be written as 1 minus X, and the denominator will give, oh no, we need, it's 1 minus, so there'll be a 2X, so we need to expand it to second order and do it. Okay, but we can just do that. Okay, and what is lambda? The thermal wavelength. Okay, but so now we are almost there. So we have this thing, and so but we need to also. So first thing to do is to compute m. We can do magnetization per unit volume. So okay, so this and the key point here is Z is kept fixed. Okay, in this computation, among other things, Z, T, etc. So what we will get is that, so all we get here is that you get a 2b from here. So you will get minus. So minus sign is already, you can see, minus c z. So that will make this a 3, a 12 root 2 lambda cubed. Okay, times, even this should be square, I think. Yeah. The EH bar by no C. Did I write C anywhere else? No. Okay. Why is that? The thing is, this is multiplied by kBt, so that will get cancelled. Okay. But we are still not done. We need to ask what is Z. We need to put in, we want to match with experiment. Okay. So for trade, Z for N. Okay. And we can use, that is one thing, but we can use the expression which we know already. For Z for it's at high temperatures for the ideal gas, it's something in terms of lambda cube. Okay. And this should be done in the limit when B is 0. We are only expanding about. Okay, so I'll just write a formula which we already know. Z equal to okay. So this is what we get. So again, I'm not very confident about the root 2 because I have put a 2 there, so we may have to figure. But I think it will sort out by itself. Where V is N by V. I think it will work out. Okay. So this is what we get. So we plug all these things. So you can see that what we have is Z by lambda cubed here. Okay. So what we get is that chi, and we will take one more derivative with respect to B. And so this implies that chi is equal to minus 1 by 6 kBt times little b times. Okay, so this is our promised formula. So we can already see the 1 by t here. Okay, just putting all the factors. Even you can see the 2a eh bar by 2m, etc. So there are these, 12 root 2 I have here. And so that's what I'm saying is that I need to, so I will not square by 6 or 12. Okay. But that's not, I mean, that is important, but I think the crucial points here are that these are that we got the 1 upon t dependence, and we also see how it depends on the various parameters in the problem. Okay, so what we now we can see that this is a diamagnetic response. What is a diamagnetism? Is that you apply a magnetic field and the induced magnetization is as the opposite sign. Okay, there are bogus derivations of this using Lenz's law, blah blah blah. I mean, those are all at some level a joke. Okay, I guess it was first done by Landau. So it's called Landau diamagnetism. Okay, so it's really, really cool in the sense that look, classically there is no magnetism, but the orbital part also gives a contribution. Spin part gives something which is paramagnetic, and we should compare, and we'll find that I think the spin part will just overwhelm the whole thing. We'll figure out. We'll see how that happens. Okay, so I think I'm done. So, but next lecture we'll do two things. We'll ask what is the magnetic response. Same question, but at t equal to 0. T equal to 0, we have to start filling up the things and ask how. So you have to go in terms of energy. So you will start filling. So first you will fill the zeroth Landau level you will fill. Okay, we'll also ignore there. I'll completely forget about the kz and say let's assume that kz is 0. Okay, that's the ground state in that, right? So we want to, if you put so and so it's like you're looking at something which is effectively a 2D gas, electrons, and now you start filling them, and as you fill them, uh, you will fill certain number of things, and the last one will be partially unfilled. Okay, so we'll start talking about filled Landau levels, and how many of them will get filled will depend on the magnetic field. So you can see, because omega c depends on B, if we increase B, what is happening is that the spacing increases, and also n dependent. I mean, that also depends. So G also depends on B. So all these things will play around in a nice way. And so as you vary B, you will see discontinuous behavior as you fill one band and go to the next one. Okay. And the second one is the paramagnetic response. From the skin. Okay. So I am done for today. But today's result is a very simple one. It says that you get a diamagnetic response for a fermi gas. That's all. Okay. So I'll pause here for questions. Nope.